Hi everyone, welcome to the third and final video going through some past exam questions on electrode potentials. If you've watched the previous two videos, you'll know what these questions look like by now. Here's a table, it's got lots of equilibria in it, it's got lots of electrode potentials in it. They all look the same, these questions really. And the first question we've got here is one that we've seen before. It wants us to draw a labelled diagram to show how we should have set this up. Okay, so again, this has been in every one of these three videos so far, so we've got to make sure that we're comfortable doing that, and we should be because it's easy. I'm still terrible at drawing, but I can still get the marks. We've got two beakers, we've got two electrodes, we've got a voltmeter to measure the voltage with, and we've got some sort of salt bridge to allow the ions to move so that the charge doesn't build up and stop the electrons from flowing. And now we need to just look at what it is we're supposed to be drawing. It's redox system 2 and 8. So redox system 2 is Fe3 plus 1. This seems to be their favourite one. This has come up at least twice already in the previous videos. So this solution is going to have, are we measuring standard potentials? Yeah, we are. So we want to have 1 mole per decimeter cubed. Concentration does matter if it's the standard potentials. So we've got 1 mole per decimeter cubed of Fe3 plus and 1 mole per decimeter cubed concentration of Fe2 plus. And therefore we're going to have to use an electrode that is made of platinum because we don't want 3 different oxidation states of iron, because that's going to make the reactions really complicated and not just the reaction that we want. The other one is redox system 8, which is this chromium one. So this is chromium 3 plus in the solution. And again, we want that to be 1 mole per decimeter cubed if it's going to be the standard cell potential, and chromium solid as the electrode. That should be it, I think. We've got our circuit, we've got our voltmeter, we've got a salt bridge, we've got the electrodes, and we've got the solutions labelled up, so I think we're good. Write down the overall cell reaction. So this is for this cell, so we look at 2 and 8. Remember, the golden rule of our electrode potentials is that the more positive electrode potential is the one that's being reduced. So in this case, we've got plus 0.77 and we've got minus 0.74. So it's definitely this one that's being reduced. So this reaction is going to happen from left to right, gaining the electrons, and the chromium is going to be oxidized going from right to left. If I write the equation that involves those two half equations, then I need to add them up so that the electrons cancel out. So I'm going to have to multiply this equation by 3. So I'm going to have 3 Fe3 plus reacting with Cr solid. We don't need the state symbols. It would have told us if it wanted us to write state symbols. And so therefore we're going to have to end up with Cr3 plus and 3 Fe2 plus. And just check the charge is balanced. We've got 9 plus, 6 plus and 3. So it's 9 plus on that side. That's good. What is the standard cell potential? This is straightforward as well. Remember, cell potentials, we just need to take away the electrode potentials from each other, find the difference between them. So we want to do this one, take away this one. Let's work this out. So it's 0.77 minus 0.74. So it's 1.51 volts for the cell potential. And so this one we need to think about a little bit more carefully. Select the strongest oxidizing agent. Now, the strongest oxidizing agent is the thing that's best at oxidizing other things. So therefore, it is the most likely thing to be reduced. Because it oxidizes whatever it's reacting with, so it is reduced. So we're looking for the thing that's most likely to be reduced. So we're looking for the most positive electrode potential. Okay. Remember, the more positive it is, the more likely it is to be reduced. So we're looking at this one, 1.33. So therefore, the strongest oxidizing agent is the dichromate ions. That makes sense, doesn't it? We know that dichromate is an oxidizing agent, but we need to be careful here. It needs to be acidified dichromate. We need to write both of these things. You can't just write that. It's the combination of the two that is the strong oxidizing agent. Okay. We don't need to write it balanced. We just say these two things. So the strongest oxidizing oxidizing agent is Cr2O7 2- and H+. Okay, and that's the same. If you think about that from organic chemistry, you have to write acidified dichromate, don't you? You can't just write dichromate. So it does need the combination of both. Okay, this question carries on. And it says, using the redox systems in that table, construct an equation for a reaction between acidified dichromate ions and methanoic acid. So here we go. So you have got a bit of organic going on here. Rather than using O or H, your equation must show the actual reactants and products. Okay, so we've got to do this properly, basically. Okay, so the dichromate ions, this one, we said this is the most positive. So this is the most likely to be reduced. So therefore, this is the one that's going to be reacting from left to right. And we want it to be reacting with methanoic acid, am I right? Yeah, with methanoic acid. So we've got to be careful here because there's two equations. Again, they've done this to try and catch us out. Look, we've got methanoic acid over here, and we've also got methanoic acid here. So we're going to have to choose the right one here. We have to be pretty careful. Okay, we want this reaction to be going from left to right, don't we? And it's going to be going from left to right anyway because it's the most positive one. But we then want the other reaction we want it to be reacting with the methanoic acid. So we want the methanoic acid one to be the reactant. If I try and react this with system number 7, so say this reacts with that, it's not going to work because this is the more positive one, this is the negative one, so this would react backwards. So dichromate, and if you see, that would make sense, wouldn't it? Dichromate would react with this aldehyde and oxidize it to make methanoic acid. You won't get dichromate reacting with methanoic acid to make an aldehyde. That's wrong, isn't it? So that doesn't work. It's going to have to be this reaction with this one, because if this is going left to right, this one's going to go right to left. So this is the reaction we want. So it's this one and this one. When we add them together, we need the electrons to cancel. So 6 electrons here means we're going to have to times this by 3. So it's going to be a bit of a faff to write here. We want the dichromate ion and 14 H+ ions. And that's going to react with methanoic acid that's been times by 3. So 3 lots of methanoic acid. And that's going to make, I'm never going to squeeze that in here. So then we're going to get 3 lots of all of this. So 3 CO2 and 6 H+. I'm going to have to cancel some of these H+ ions out, aren't I? I was wondering why it was 2 marks. So we have to cancel this. So 3 of that and 6 of that, and then these products. So 2 Cr3+ and 7 H2O as the other products. Okay, and so then we need to then just cancel out the H+ ions. So we will cancel that out and cancel that and make it 8. Okay, and I'll probably write it out again just to make it clear. It's worth it for the sake of, 20 seconds. It's probably worth doing this. Just so you don't lose a mark for something that you did actually do correctly. It doesn't take long to write that out again, does it? Okay. Right, it then says they added some chromium metal to an acidified solution containing copper 2 ions and a reaction took place. The student concluded that chromium is more reactive than copper. Explain in terms of the electrode potentials why chromium is more reactive than copper. Okay, so let's go and look at the electrode potentials then. So we've got the copper one here, and it's plus 0.34, and the chromium one then is this one at the bottom, presumably. They added, chromium metal, so solid chromium. So just because I was looking here, we've got chromium up here as well, but there's no solid chromium in that one, so it must be this one. So we added solid chromium. Yeah, this makes sense, doesn't it? We added solid chromium to a solution of copper 2+. And this does make sense because the copper's electrode potential is more positive. So it's the one that would be reduced and the copper would be oxidized. Okay, so that's what we want to write, that the electrode potential for redox system 5 is more positive than redox system 8. for redox system 5 is more positive than the electrode potential for redox system 8. So therefore, what's going to happen is that copper, if we go back to look at this, the copper equilibrium is going to be going from left to right, and the chromium equilibrium is going to be going from right to left. So actually the most sensible thing, yeah, let's just write the equations out, because then it will show what's happened is basically a displacement reaction then, isn't it? Chromium's displaced the copper, and you end up with chromium in the solution, and copper would come out as the solid. So let's write this in. So what would happen? So the reactions, I would perhaps just write this all as one equation. Now let's do it as two separate ones, just so we know what's happening with each equilibrium. So the reactions would be the copper would react from left to right, so that would be Cu2 plus 2 electrons going to the copper as the solid, so the copper would be displaced as a solid, and the chromium would be the chromium solid going to Cr3 plus and losing 3 electrons. I think it's probably nicer this way because it shows what's happening to each one, including the electrons. Whereas if we combine them together, it perhaps wouldn't be so clear what's going on. I think that's plenty. We've done an explanation. We've written 2 equations. If we're not getting 2 marks for that, I think I'd be very annoyed. Okay, and then finally the last bit here, methanoic acid has the name of formic acid, direct formic acid fuel cells. I mean, why would you do that? That's a DFAFCS. It's a horrible acronym. Being developed for use in things. Methanoic acid reacts with oxygen to generate a cell potential. Predict the standard cell potential. Okay, so again, we're going to have to go back and look at the electrode potentials and find one that involves methanoic acid and one that involves oxygen. So let's have a look. Right, methanoic acid, we've seen these before. We've got 2 options, haven't we? It's either going to be 6 or it's going to be 7. But it needs to react with oxygen. So where is there oxygen? There's oxygen here. So we want oxygen to be the reactant. So we want this redox system 4 to go from left to right. So that would have to be the more positive one. And we'd want the other one to go from right to left. So we want the methanoic acid to be on the right. So it'd have to be this one. Okay. Because if we use this one, this would not react. It would go from right to left. So it would be this as the reactant and this as the product, which wouldn't work. We want it to be going right to left. So we want methanoic acid as the reactant. So therefore it's going to be 4 and it's going to be 6. What was the question? Predict the cell potential. Okay, so if it's 4 and 6, then it's going to be 1.23 minus 0.22. I could have done that in my head, probably 1.45. So the cell potential would be 1.45 volts. Okay, a couple more questions to show you. Again, these questions all look the same. I have said this before. Here's a table full of electrode potentials. We've seen this bit of the question before. Again, I make no excuses for showing you these again. Look, you need to make sure you can draw cells. We need to make sure we can do definitions like standard electrode potential. So we've seen this before. This is the EMF, the electromotive force of a half cell compared to the standard hydrogen half cell. You've got to know that definition. It comes up regularly. And include the standard conditions. So it's 298 Kelvin. It's 100 kilopascals for the pressure. And the solutions need to be 1 mole per decimeter cubed. And we've got to make sure we're comfortable with that. Okay, electrochemical cell can be made from redox systems 1 and 2. Write down the standard cell potential. Okay, again, we've seen this question come up loads, can't we? We need to make sure we can do this. This is easy, hopefully. So 1 and 2, we do the positive one, take away the negative one. So it's going to be 0.34 minus minus 2.37. So it is 2.71. Okay. Right, and then the last question at the page here says, using redox systems 3, 4, and 5 only. Okay, so we've got to just use those. Predict 3 reactions that might be feasible. Okay, and write the overall equation for each reaction. Okay, so 3, 4, and 5, 3 reactions. Okay, so this is going to be 3 reacting with 4, 3 reacting with 5, and 4 reacting with 5, isn't it? Those are going to be your 3 reactions. So 3 and 4, which way around is this going to be? Out of those, 4 is the more positive one. And with the golden rule of all of these things, the more positive one is the one that's going to be reduced. Okay, so therefore 4 is going to react from left to right. We have Fe3 plus going to Fe2 plus, and 3 is going to be backwards. So it's going to be Fe3 plus reacting with Al, but we need to make the electrons balance, so we're going to have to multiply this bottom one by 3. So it's going to be 3 Fe3 plus Al. And that is then going to make Al3 plus and 3 Fe2 plus, because we times this by 3, haven't we? And again, check the charges are balanced. We've got 9 plus, 6 plus, and 3 plus 9 plus. So that was 3, and that's right. This is 3 and 4. This is going to be 3 and 5, and this is going to be 4 and 5. Okay, so 3 and 5. 3 is this aluminium one again, it's minus 1.66. 5 is plus 0.54. So again, this is going to be the forwards reaction, left to right, and the aluminium is going to go backwards. So it's going to be I2 reacting with aluminium, but we've got 3 electrons and 2 electrons here. So we're going to times this by 3 and times that by 2. So it'll be 3 I2 and 2 aluminium. It's going to end up with 2 Al3 plus, and we times this by 3, didn't we? So 6 I minus, 2 Al3 plus and 6 I minus. Again, check the charges. We've got no charge on the left-hand side, and we've got 6 plus and 6 minus on the right-hand side, so that cancels out. So that's fine. And then finally, 4 and 5. So out of these two, it's the iron that's the most positive one. So that's going to go from left to right. That's going to be reduced. The iodine is going to be oxidized. And if we combine these two together, we just need to times the iron by 2. So this is going from left to right. So it'll be 2 Fe3 plus 2 I minus. And that is then going to give us I2 plus 2 Fe2 plus. And again, let's just check the charges. We've got 6 plus and 2 minus. So that's 4 plus, and we've got 4 plus on that side. Okay. Lovely. Then there is actually a question we haven't come across before here. This was an important question. That's why I wanted to make a third video with this one in it. Give 2 reasons why it's uncertain whether reactions predicted from electrode potential values may actually take place. So we've just said this is a reaction that's going to happen, but why might that not actually happen? Okay, there's 2 reasons. One is to do with rates of reaction. That, okay, yes, technically that reaction should happen, but it's just so slow that it's not going to look like anything's happening. And the reason it would be a really slow rate of reactions if the activation energy was very high. So that would be one reason. It's just such an energy barrier for that reaction to happen that realistically it doesn't actually happen. And then the other reason is we're making these predictions based on the standard electrode potentials, but those will only work if you're doing it under standard conditions. Okay, and hopefully you've seen this in other aspects of chemistry, that whenever it's why is it not what you think it should be, very often the answer is that you're not doing it under standard conditions. You'll have seen that with enthalpy changes before. Right, then we're saying in aqueous acid, Cl- ions react with chlorate ions to form chlorine gas. Oh god, there's just chlorine everywhere in this question. This is going to get very confusing. right, chloride reacts with chlorate to make chlorine, whereas in alkali, it's the opposite. Okay, explain this difference, use table 7.1. Okay, well, it's going to be just whatever's going on with the electrode potentials again, isn't it? One way it's one way round, one way it's the other. So what are we looking at? Chlorine. Right, it's going to be these bottom two, isn't it? So what would we expect? We'd expect the bottom one is the more positive value. So we would expect that to be reduced if it's more positive. So we'd expect that to go from left to right, and this number 6 to go from right to left. So we would expect ClO minus and H plus to react with Cl minus and form chlorine gas. Yeah, that's this. In aqueous acid, so when we've got acid, when we've got H plus ions, ClO minus would react with chloride ions to make chlorine gas. So that makes sense. We can explain that just from the electrode potentials. Okay, so let's say that the electrode potential of system 7 is more positive than system 6. The electrode potential for redox system 6. And then it doesn't say we actually need to write equations, does it? So let's just, yeah, it doesn't want the equation. They've kind of told us what the equations are going to be anyway. So let's just talk about the equilibria. Let's just say, so therefore, the equilibrium in redox system 7 would shift to the right, because we'd be doing the reduction, and the equilibrium in redox system 6 would shift to the left. Okay. So the equilibrium in redox system 7 shifts to the right, and the equilibrium in redox system 6 shifts to the left. Okay, but if we've then got it in alkaline conditions, then it's not going to be able to work, is it? If we've got alkali, then we're not going to have H plus ions. So we're going to force this equilibrium to go from right to left. It can't possibly go from left to right because it's not going to have any H plus ions, because it's in alkaline conditions. They're all going to have been neutralized. So it would then have to be the other way around. Okay. So that's what we can say. We can say in alkaline conditions, H plus ions are removed. So it's going to be the opposite way around. I'm not sure I'm going to fit. I think I waffled a bit too much here. H plus ions are removed. So let's just shorten this down. So therefore 7 is going to have to shift to the left. And 6 shifts to the right. Then they're both going to have to be the opposite way around, right? And then again, we want to link that to the electrode potential. So what that would mean then is if that is shifting to the left and that is shifting to the right, is because this electrode potential then, this would not be the right value for the electrode potential. Okay? Because if we keep those values, then it should still be happening the same way round. But if we get rid of all the H plus ions, we're then not understanding conditions anymore, are we? Because we've changed the concentration. So this electrode potential is not going to be the same value. And it would be at a value that would be less positive than that. And that's then why the equilibriums would be shifted the opposite way around. Okay. The electrode potential for 7 would change to a value less positive than the electrode potential for 6. Okay. Okay. Right, then it says in acidic, so here we go, a similar thing with acidic conditions, so there's going to be H plus ions involved here. SN2 plus ions react with IO3 minus to produce iodine and SN4 plus. What is the oxidizing agent in this reaction? Okay, so the oxidizing agent is the thing that oxidizes something else. So what has been oxidized? Well, the tin has been oxidized, and it's gone from SN2 plus to SN4 plus. So the tin has been oxidized. So whatever this reacted with must be the oxidizing agent. So it must be the IO3 minus. Okay. So IO3 minus is the oxidizing agent because it oxidizes SN2 plus to SN4 plus. And then we're going to have to say how, basically. So if it's an oxidizing agent, then what it's done, it's been reduced, so it has gained electrons, okay, by accepting electrons. Yeah, it's oxidized this, so it's been reduced, so it's gained electrons from SN2 plus. Right, then it says construct an equation for this reaction. So this is just a redox question, really. Have they given us, I'm just looking, can we go back to electrode potentials? No, we haven't got tin and IO3 minus, no. So I was wondering if we could do it off of this, but we're actually going to have to work it out ourselves. It's always worth checking that. You know, if they've written the half equations out for you, it makes your life a lot easier. But they haven't given us those, so we're going to have to work this out ourselves. So let's have a go at doing this equation. I always do a rough first, and then we want to do two half equations and add them together. So we know we've got SN2 plus ions reacting with IO3 minus to produce iodine. Now iodine is I2, isn't it? And SN4 plus. Right, then let's look at the oxidation numbers. Okay, we know that this is +2 here, going to +4. So the tin has been oxidized. We knew that anyway, didn't we? So therefore, we can write a half equation that involves the tin, and that's going to be easy. It's just SN2 plus going to SN4 plus 2 electrons. That's a nice easy half equation. The other half equation is going to involve the iodine, whatever business is going on here. So let's look at the oxidation numbers. Here, the iodine is obviously 0 because it's an element on its own. What's the oxidation number going to be here? Well, oxygen is always -2, isn't it? Times by 3 is -6. It needs to add up to -1, so the iodine must be +5. So the iodine's going from +5 to 0. Okay, so this other half equation is going to involve the IO3 minus going to I2. This is being reduced, so it must be gaining electrons. And it's gaining 5 electrons to go from +5 to 0. But we need to be careful because it's making I2. We need to make sure the iodines are balanced, right? It must actually be 2 IO3 minuses. So we've got 2 iodines there. And so if it's gaining 5 electrons, it's actually gaining 10 electrons, isn't it? 5 for each iodine. And then we need to complete this half equation by balancing the oxygens. So I've got 6 oxygens on this side. So I need to have 6 H2O to balance that. And that gives me 12 hydrogens. So I need to have 12 H plus to balance those. And just check then that we've got the charges balanced. There's no charge on this side. 12 plus minus 10 is 2 plus minus another 2. So there's no charge on that side either. Okay. So those are our two half equations. Now we can combine them together. Before we do that, we need to make sure that the electrons cancel each other out. So we're going to have to multiply this half equation by 5 to get 10 electrons. So now we can add them together. It's going to be 5 SN2 plus 2 IO3 minus. 10 electrons would cancel out. Plus the 12H plus is going to make I2 plus 6 H2O plus 5 SN4 plus. That's our overall equation.